Okay, what we're going to look at today is what we call roots of unity. And that is solutions to the equation z to the power of n equals, most of the time will be 1, but could also be minus 1. So, now, I've mentioned this yesterday when we were talking about, or was it the day before, when we were talking about roots and de Moivre's theorem, that when you place them on the Argand diagram, they'll be evenly spaced around the Argand diagram. So this particular one, because it's z to the power of n is equal to plus or minus 1, we know the modulus is always going to be 1, because the nth root of 1 is always 1. So we know they're going to lie on the unit circle. And so if we were to join up all the solutions, we'd end up with a regular n-sided polygon. So 4 solutions, we get a square and so on. So z to the power of 5 is equal to 1. So I can use our de Moivre's idea. Notice, instead of going 0, 1, 2, 3, 4, I've decided to go 0 plus or minus 1 plus or minus 2. And the reason I've done that is because one of the things I do know about solving polynomials is that if there are going to be complex solutions, then solutions will always appear in conjugate pairs. Now, the reason for that is we can always factorize down to a quadratic or a linear function. And a quadratic, we would use the quadratic formula and go plus or minus the square root of. That's going to be the imaginary bit. So you always end up in conjugate pairs. And so that's why it's useful to sub in plus or minus rather than the 3 and the 4. Because it'll get you to the conjugate straight away. One will be positive in angle, one will be negative in angle, and so on. So here's our solutions. Cis 0 is obviously a solution. Then cis 2 pi and 5, which means cis minus 2 pi and 5, because they'll be in conjugate pairs. Cis 4 pi and 5, which means cis minus 4 pi and 5. That rule about conjugate pairs, by the way, only true if the coefficients in the polynomial are real. Which obviously this one is, because it's just simply z to the power of 5 is equal to 1. So if I was to place it on the Argand diagram, well, there's 1, or cis 0. Next one, cis 2 pi and 5, its conjugate would be reflected. Next one, cis 4 pi and 5, its conjugate, again, is reflected. There we are, we get our lovely pentagon if we were to join them up, and they all lie on a circle, the unit circle. All right, let's stick with this particular problem then. So omega is going to be one of the complex roots. Now, when they say the complex root, they're talking about the root that contains an imaginary part. Okay? So, in other words, it's not 1, it's one of the others. Okay? We're going to also show that omega squared, cubed, 4, and 5 are the other roots of the equation. Now, you might think, oh, well, that's all right, I'll just substitute in one of them and then show. But remember, they're just saying one of them. It's not saying which one. So unless you were to substitute in all 4 and test them, and that's a lot of work, then you can't do it that way. Here's how we do it. Z to the power of 5 is equal to 1. Now, if omega is a solution, then it must be true that omega to the power of 5 is equal to 1. Okay. Well, omega to the power of 5 to the power of 5, therefore, is 1 to the power of 5. 1 to the power of 5 is 1. So omega to the power of 5 is also a solution. Because when I substitute it into z to the power of 5, I get the answer 1. Okay? Now, omega squared to the power of 5 is the same as omega to the power of 5 squared. And omega to the power of 5, we've said, is 1. So that's 1 squared, and that's 1. So omega squared is a solution. Because when I substitute it in to z to the power of 5, I get the answer 1. So omega squared is a solution. Omega cubed to the power of 5, I could rewrite as omega to the power of 5 to the power of 3. Omega to the power of 5 I know is 1. And 1 cubed is 1. So, omega cubed is also a solution. And omega to the power of 4 to the power of 5 is the same as omega to the power of 5 to the power of 4. But I know omega to the power of 5 is 1. So that's 1 to the power of 4, which is 1. So omega to the power of 4 is a solution. So I've now successfully shown they're all solutions without actually naming which particular one omega is. As long as omega is a solution, they will all be solutions. So therefore they are all roots to this equation. So now we're going to prove 1 plus omega squared plus omega cubed plus omega power 4 is equal to 0. Well, I could do it this way. I could say, well, that's the sum of the roots. Because remember, omega to the power of 5 was equal to 1. So really, I've got the sum of all the roots there. Omega squared, and so on. Well, that's minus b on a. Now, in our polynomial, minus b, well, there is no power to the 4 term there. So that's equal to 0 by the sum of the roots. Done. That's one way we could do it. So there's our equation. Omega to the power of 5 minus 1 is equal to 0. I could factorise that. Remember we generalised our difference of 2 squares, difference of 2 cubes. We said, we could always factorise it. The first brackets or parentheses will be omega minus 1. And then in the second one, it'll be all the other ones where the powers of omega are going down by 1 and so on. So we'd end up with omega minus 1 outside of 1 plus omega squared plus omega cubed plus omega power of 4 is equal to 0. This has two possibilities. So there's our general formula, just to remind you there. That's where I've grabbed that from. Well, it has two possibilities. One possibility is that omega is equal to 1. Yet we've specified omega is not equal to 1, because we said it's the complex root. It's not the one where omega equals 1. Therefore, the only other possibility is the other parentheses is equal to 0. So 1 plus omega squared plus omega cubed plus omega power of 4 is equal to 0. So that's another way we could do it. Another way we could do it. What do we got there? It's a geometric series. So I could say, well, the first term is 1. The ratio is omega. The number of terms I've got is 5. So if I sub that into our formula for sum to 5 terms, I get 1 outside of omega to the 5 minus 1 over omega minus 1. But hang on, omega to the power of 5, we know that's equal to 1. So that equals 0. So there's a third way we can solve that particular problem. So each one approaching from a different way. One using our series ideas, one using polynomial ideas, and one just using basic factorisation. All right. We're now going to find the equation whose roots are omega plus omega to the power of 4 and omega squared plus omega cubed. And remember, I don't know what omega is. I just know it's one of them. Could be any of them. Okay, sum of the roots. Well, the sum of the roots will be omega plus omega to the power of 4 plus omega squared plus omega cubed. Oh, well, I know what that is now. Because remember, we just proved 1 plus omega squared plus omega cubed plus omega to the power of 4 is equal to 0. Therefore, that is negative 1. So I know the sum of the roots. Now all I need to create the quadratic is the product of the roots. So product of the roots. All right, let's expand this out, see what we get. Omega cubed plus omega power of 4 plus omega power of 6 plus omega power of 7. But I can simplify that because I know omega to the power of 5 is equal to 1. So omega to the power of 6 is the same as omega. And omega to the power of 7 is the same as omega squared. And so I've got omega cubed plus omega to the power of 4 plus omega squared. Oh, that's equal to negative 1. So they both equal to negative 1. So we're talking about the quadratic whose sum of the roots is negative 1. Product of the roots is negative 1. So it must be x squared plus x minus 1 is equal to 0. And there's the quadratic. Now, the reason why they ask them to do it in these pairs, they turn out to be the conjugates. It doesn't matter which one you pick for omega, omega to the power of 4 will end up being the conjugate of the one you picked. And same with omega squared and omega cubed. If you picked one of them and said, okay, that's going to be omega squared, it will turn out omega cubed is its conjugate. Basically, the conjugates in these roots of unity question, the powers will always add up to be the power of the question, in this case 5. So if you're trying to work out, oh, well, how do I group conjugate pairs together? Just look at the powers. They've got to add up to 5. Okay. If omega is a complex cubed root of unity, so this time it's a solution to z cubed is equal to 1. Use the fact that 1 plus omega squared is equal to 0. So we don't have to prove it this time. They've given it to us that the sum of the roots is equal to 0. We're going to evaluate 1 plus omega squared all cubed. In a roots of unity question, you only ever know 2 things. And with those 2 things, you should be able to solve any question. That is, z to the power of n is equal to 1. In this case, z cubed is equal to 1. And the other one is that 1 plus omega squared plus omega cubed plus omega, however many you have to go up to, is equal to 0. Using those 2 things, should be able to solve it. So in this case, well, they've told me that 1 plus omega squared is equal to 0. The other thing that I know, omega cubed is equal to 1. Using those 2 ideas, I should be able to solve this. So we have to evaluate 1 plus omega squared to the power of 3. Could expand the whole thing out, not going to. It's easier to cube 1 term than it is to cube 2 terms. I can rewrite 1 plus omega squared. It'll be minus omega, and it's still cubing it. So now all I'm saying is, what is minus omega cubed? Oh, well, omega cubed 1, answer's minus 1. Now, had I expanded the whole thing out, you still would have got minus 1. But obviously, there's a lot more terms to play with there. Evaluate this expression, 1 on 1 plus omega plus 1 on 1 plus omega squared. So we've got algebraic fractions, but again, a lot easier, instead of working with 2 terms, to work with 1 term. So I can rewrite those fractions. 1 plus omega would be the same as minus omega squared. And 1 plus omega squared would be the same as minus omega. So now I'm just saying, what is minus 1 on omega squared minus 1 on omega? Well, the common factor, or common denominator, I should say, is omega squared. So the top becomes minus 1 minus omega. But minus 1 minus omega would be the same as omega squared. And so omega squared and omega squared, the answer is 1. So each time, all I'm doing is using the fact that 1 plus omega squared is equal to 0, or I'm using the fact that omega cubed is equal to 1. Form the cubic equation that has roots 1, 1 plus omega, and 1 plus omega squared. Okay. I know 1 is a solution. So therefore, I know z minus 1 is a factor straight away. So really the question now is, form the quadratic whose roots are 1 plus omega and 1 plus omega squared. Now, I could have made life easier for myself, but I thought I'd do it the long way this time, just to show you it does work just as well. I could have said, well, 1 plus omega is the same as minus omega squared, and 1 plus omega squared is minus omega, and then I've got less to work with. But either way, remember, the quadratic will always be minus the sum of the roots. The sum of the roots here is 2 plus omega squared. Z plus the product of the roots. If I multiply 1 plus omega with 1 plus omega squared, I get 1 plus omega squared plus omega cubed. Let's simplify that. Remember, we only know 2 facts. I've got 2 plus omega squared, but I know 1 plus omega squared is 0. Therefore, that must equal 1. And then the other one, I've got 1 plus omega squared, well, that's 0, plus omega cubed, well, omega cubed is 1. And so there it is factorised. Z minus 1, z squared minus z plus 1 is equal to 0. Now, form the cubic equation. I mean, that's it, factorised. I expanded the whole thing out just to make it look like an interesting equation, but it probably could have stopped at the factorised form. And tidy up, there it is. Nice symmetry about it too. We're going to solve this particular equation, which looks really difficult, but it's actually quite easy using roots of unity. There's that pattern again. We've got all the powers, 1 plus z squared plus z cubed plus z to the power of 4 plus z to the power of 5. Now, I know z to the power of 6 minus 1 would be that sum there times z minus 1. Okay? I know that to be true. I can also find the solutions to z to the power of 6 minus 1 very easily because it's just the roots of unity question. So I'm going to do that. Notice again, I'm saying, well, I know they're going to be in conjugate pairs. So I'll go 0, because I know 1 is a solution. Conjugate pairs, plus or minus 1, plus or minus 2. I need 6 solutions all up. So I don't use plus or minus 3, I just pick one of them, and I've chosen positive 3. So I've got 6 possibilities, consecutive solutions. So subbing in, oh, not subbing in, sorry. This is the equation we have to solve. I've now rewritten it like so. I've multiplied top and bottom by z minus 1. The top of the fraction is z to the power of 6 minus 1 is equal to 0. But if I'm solving a fraction equaling 0, it must be the top of the fraction that equals 0. And I know the answers to z to the power of 6 minus 1 equals 0. The only thing I know is, hey, it's going to have 5 solutions, not 6 solutions. Which one don't I use? Well, clearly the one on the bottom, because the bottom of the fraction can't equal 0. And so that's why I say, well, all right, it's going to be all the solutions of z to the power of 6 minus 1 equals 0, but not the solution 1. So therefore, it must be all the other solutions. So cis pi and 3, its conjugate. Cis 2 pi and 3, its conjugate. And cis pi would be the other solution. And if I want to be really fancy, let's take them out of mod arg form. And we've got half plus root 3 on 2i and so on. Okay, it's an old question. In this case, they told me which of the solutions omega is. So it's going to be cis 2 pi on 9. And what it's saying is we're now going to show that omega to the power of k is always a solution of z to the power of 9 minus 1. But because I now know the specific solution, it makes life a lot easier, because if z to the power of 9 is equal to 1, then I'd say, oh, well, z is equal to cis 2 pi k on 9, where k is, and this time I have listed all them all out, 0, 1, 2, 3, up to 8. Well, I could rewrite cis 2 pi k on 9 as cis 2 pi on 9 to the power of k. But cis 2 pi on 9, they've told me, is omega. So it's omega to the power of k, where it's 0, 1, 2, 3. So I've just shown that omega to the power of k is a solution. Now I could do it that way because I knew which particular solution omega was. The one before I didn't know, and so I did it that way of playing with the indices to show they all were. Again, there's the standard question, just written slightly different. Prove that omega plus omega squared, and so on and so on and so on, up to omega to the power of 8 is equal to negative 1. Well, we've got the equation z to the power of 9 minus 1 is equal to 0. Therefore, 1 plus omega and so on is equal to 0 because it's the sum of the roots. So I chose that particular method this time. Now I just move the 1 to the other side, and I've got the expression I want. Hence show cos pi on 9 times cos 2 pi on 9 times cos 4 pi on 9 is equal to 1/8. This is good. You're going to love this. Okay. Z to the power of 9 minus 1. I know it factorizes like so because they're all the roots. So I could say it's z minus 1, z minus omega, z minus 8. And you might think, oh, that's an interesting way of doing it. Why didn't I just go 1, 2, 3, 4, 5, 6, 7, 8? I'm grouping conjugates. Remember what I said about the powers? So you'll notice it goes power of 1 with, well, power of, 9 that would be. Oh no, sorry, power of 0 with power of 1. But, oh no, I've grouped it. Start again. I've said that wrong. Started with z minus 1 because we know 1 is a solution. Then becomes my conjugate pairs. 1 and 8 make 9. 2 and 7 make 9. 3 and 6 make 9. 4 and 5 make 9. So they're all in conjugate pairs. So because they're in conjugate pairs, when I expand them out, then I know it's going to be, the sum of the roots will be twice the real part. The product of the roots will end up being 1. So each one of these, I've now got minus twice the real part, z plus 1. The next one, minus twice the real parts, and that one's 4 pi on 9. Next one, twice the real part, but that's 6 pi on 9. Next one, twice the real part, but that's 8 pi on 9. So there is our equation. Z to the power of 9 minus 1 is equal to this. What happened? Do you notice the difference? What's changed between the two lines? There is a difference between it. Can you spot the difference? Right. Because, think about it, cos 6 pi on 9, what's 6 pi on 9? 3 pi on 2. So it's I, minus I. So I subbed in, and we ended up with our z squared plus z plus 1. Okay? We're going to let z equal I. If we sub I in, we will get this. I to the power of 9 minus 1 is equal to I minus 1 minus 2 cos 2 pi on 9 I minus 2 cos 4 pi on 9 I minus 2 cos 8 pi on 9 I. Because all of these z squared plus 1s become 0. So I'm just left with the middle term in each case. All right, so this is where we're at. So I minus 1 will equal, now I factorised I out of each of them. And so I get I to the power of 4, or minus I to the power of 4, because I factorised the negatives as well. Well, I to the power of 4 is equal to 1. And then I've got an I minus 1, which will cancel with an I minus 1. And I'm now left with 8 lots of cos 2 pi on 9, cos 4 pi on 9, cos 8 pi on 9 is equal to negative 1. Almost there, because they want a pi on 9. So I'm going to play with the 8 pi on 9. 8 pi on 9 is in the second quadrant. So it's the same as the negative. The cos, the acute angle would be pi on 9. And so eventually we get an answer. Told you you'd enjoy that. All right. Okay. Well, let's play with these roots of unity and see how we go.